We'd like to thank you for joining Moleaer's webinar on the future of wastewater, how do nanobubbles improve treatment efficiency and reduce costs. I would like to introduce you to our speakers today. First up is Andrea White. Andrea leads our Moleaer's wastewater process engineering group. She has a vast experience in designing wastewater plants and has been with Moleaer for over 5 years. She spearheads our understanding of the nanobubble applications in multiple industries, and especially in the biological treatment of wastewater. John is our operations guru. He's a former customer of Moleaer who was so excited to implement the technology and saw the benefits that he joined us to spread the word. He's a natural tinkerer, and he's always attempting to find solutions to these complex challenges we're trying to solve. He helps in applications development and solving customer problems. John, Andrea, the floor is yours.
Thank you, Baji. I'd like to start with our first poll question. Which wastewater treatment challenges are most important to you? Select all that apply. Reducing chemicals and energy, reducing odors and corrosion, increasing treatment capacity, increasing biogas, improving effluent water quality, or other. And if you select other, please text and specify your response in the box provided on your screen. Well, there are some clear leaders in this group. At 77%, we have reducing chemicals and energy. At 60%, we have improving effluent water quality. At 44%, increasing treatment capacity. And then in the 20 percentiles, we have reducing odors and corrosion and increasing biogas. So that brings us to what we're going to be covering today. So by the end of this webinar, we hope that you have learned a bit about Moleaer's clean chemistry, specifically how to describe the operational and cost benefits achieved using Moleaer's technology to remove inhibitory compounds. You will also be able to identify common inhibitory compounds and explain how they disrupt wastewater treatment processes. Additionally, you'll be able to describe how Moleaer's technology selectively targets and breaks down these inhibitory compounds. And most importantly, you'll be able to identify the specific benefits that Moleaer's technology can bring to your wastewater treatment facility. Moleaer was founded in 2016. We began manufacturing nanobubble generators, starting with low-flow nanobubble generators. We have over 150 low-flow nanobubble generators installed across the globe, treating wastewaters both industrial and municipal. A couple of years ago, we scaled the technology to create a high-flow system. We now have multiple installations across the US and Europe for our high-flow wastewater installations, including municipal wastewater, but also including industrial wastewater, such as dairy wastewater and poultry slaughterhouse. So what are the visual effects of Moleaer's clean chemistry? Well, you can see here in a side-by-side comparison on primary clarifiers. So rectangular primary clarifiers. The clarifier on the left is not receiving injection of Moleaer's clean chemistry. The clarifier on the right is. Prior to receiving Moleaer's clean chemistry, both of these basins had a stable scum layer of 5 inches. Within 1 week of treatment, Moleaer system was able to completely remove or break down that 5-inch scum layer. We see a similar effect on lagoons. At the beginning of treatment, a stable scum layer. Within 1 week, much less of a scum layer. And after 2 weeks, almost the complete removal of the scum layer. We also see this effect when we're looking at equalization basins and other basins. Before Moleaer's technology is applied, a stable layer of foam. After Moleaer's technology is being applied, we see almost the complete removal of that foam layer. So what does this translate to in terms of cost savings and other benefits? You see here on your screen a chart depicting the average annual energy savings of around 15% when using Moleaer's technology. That's the total plant energy in terms of kilowatt hours per kilogram BOD removed. We see this across multiple installations. Other measured benefits are reduction in aeration energy requirements, over 40% reduction, as well as a reduction in disinfection chemicals, saving over 40% on chlorine. We see an improvement on primary clarifier solid separation, providing 10% more solids removal. Additionally, for activated sludge systems, we see an increase in secondary treatment capacity of 20% or more. And in anaerobic digestion, we see improvements there too, improving biogas quality and quantity with up to 20% more methane. Which brings me to the second poll question. This second poll question is the same as the first one, but this time we would like you to just select one. Which wastewater treatment challenge is most important to you? Reducing chemicals and energy, reducing odors and corrosion, increasing treatment capacity, increasing biogas, or improving effluent water quality. Again, if you select other, please specify by typing in your response. Again, in the first place position at 43%, we have reducing chemicals and energy. And then to lesser percents, we have improving effluent water quality and increasing treatment capacity. John, as an operator, can you tell us a bit more about what can be done to help reduce chemicals and energy?
Absolutely. Thank you, Andrea. Now that we have discussed some of the common problems that you have at your wastewater facilities, let's go a little bit deeper into all the problems and really reveal what the root cause is. So rising energy and chemical costs are largely outside of our control, but it's a global issue that we're seeing both in the US and across Europe. Fog, scum, and odor issues are always a high importance to us, as we have to be good to our neighbors, making sure that we're not creating a nuisance. Frequent process upsets and inconsistent performance. This is something that's starting to plague us across the industry. And oftentimes we don't know why, but it's definitely periodic, and it causes issues with nitrification and with methane production. Bulking sludge, filaments, bacterial problems, and poor settling sludge are another issue that is common to our wastewater treatment plants. And oftentimes we're holding a lot more sludge under aeration to hopefully meet the previous problem with inconsistent performance. We're also running into treatment capacity constraints. Globally, populations are increasing within the existing cities. Normally, when cities expand and grow, there's plenty of money that's given to increasing the infrastructure as well. But what we're seeing at wastewater treatment plants and at the plant that I used to work at is that we're at our solids loading capacity for the wastewater treatment plant at nearly half the hydraulic flow. Lastly, as we go to attaining net neutrality on our energy usage, biogas quality is the most important. We need to be able to generate as much electricity on site. So what is the root cause to a lot of these problems? It's an odd word for some of us, but we'll explain it a lot more. But these are all caused by amphiphilic compounds. They interfere with solid separation, with biological treatment process, and most importantly, with efficient oxygen transfer. So where do these amphiphilic compounds come from? Well, some of them are natural and are part of our wastewater, such as fats, oils, grease. But some of them, and most of them, are man-made chemicals that help enable our lives, making our lives more productive, such as soaps and surfactants. These chemicals are found in our shampoos and conditioners, in our body wash, everything that we use to remove oils, such as laundry detergent and dishwasher detergent, contain a single common surfactant. The most common of them is sodium lauryl sulfate. but we also use all sorts of other surfactants in industrial settings, such as surface cleaners and degreasers. Lastly, a different branch of surfactants are called quaternary ammonium compounds, and the most common of these is benzalkonium chloride. These are very common disinfectants used both residentially, commercially, and in industry for clean-in-place procedures for the food and beverage industry. These QAC compounds are what really helped us through the pandemic when we talk about surface cleaning. If you look for benzalkonium chloride, you're going to find it on a lot of your surface cleaning products. So how do we measure these compounds in wastewater treatment facilities? Well, from my experience, it's very difficult. I wanted to know where these chemicals were coming from, and I wanted to test them in the wastewater. But what I found was that there are a lot of field kits available, but typically they're for measuring these compounds in clean water. When we talk about surfactants, there's both positively charged cationic surfactants, negatively charged anionic surfactants, and non-charged surfactants. Unfortunately, for many of our field measurements, they have positive and negative interferences for each other. And we have all of these chemicals coming in to our wastewater. There are lab methods. Unfortunately, they're expensive and it takes a long time to get results. So it's not really actionable. But ways that we know that they're coming to us, and we know that they're coming into every wastewater treatment plant. It's just the matter of how much and when. But you can look at plant power draw, your blower draw, DO concentrations through the plant, increases in biological oxygen demand, BOD, or chemical oxygen demand, COD, and also fats, oils, and greases. One thing that's important to do is look at your plant, go walk around. A lot of these things can be really obvious. Odors, foam, scum. If your wastewater is normally coming in a nice light gray color and all of a sudden it's black, something has changed. What has changed in the energy used around the plant? This is another great sign. Process upsets, especially regular ones occurring weekly. They don't have to be big, but just noticeable and regular. Sometimes the effects are DOs go up and treatment quality goes down. Other times we see that DOs go down as loading increases, a more natural response. But ultimately there's declining effluent water quality and we end up using more energy and more chemical. So how do these amphiphilic compounds, soaps, and surfactants work? Well, the symbol to the left shows the basic chemical shape of a surfactant. It has a hydrophilic head, that means it likes to be in water, and a hydrophobic tail, that means that it wants to stay out of water. What's unique about these compounds is they're able to accumulate or surround other hydrophobic chemicals in wastewater, ultimately allowing them to be washed away using water. So when we think about a simple example of washing your oil off your hands, if you try to wash with just water alone, the oil sticks to your hands. The same occurs when cleaning plates and greasy dishes. You need a surfactant to be able to pull those oil compounds away from your skin or from your plate and be able to wash them away with the water. Well, this washing them away with the water means that we're sending a lot more surfactants and oil and grease to our wastewater treatment plant. Ultimately, stronger detergents and less water use means more surfactants in wastewater. So how does this look as the wastewater comes to our plant? Well, this triangle kind of demonstrates the different ways that we can look at surfactants and oil in water. Let's assume that the water coming to our plant stays the same. Let's just look at the changes as we add in more surfactant. So at the bottom left, we can see when we have just oil and water and no surfactant at all, we get great separation between the oil and the water. Unfortunately, if you're a facultative lagoon and you're depending on surface transfer of oxygen, you can see that that oil has a very strong barrier over the top of the water. As we add in an extreme amount of surfactant, we get what's in the top left corner of this diagram. And this is our scum. These are our fatbergs. This is what looks like when solids accumulate. And this is a stable emulsion that we call a gel when we have a lot of oil and a lot of surfactant together. But what's most common to what's coming into our wastewater treatment plant is what we see on the right-hand side. This is a more stable emulsion of both oil, surfactant, water. You can see there's a little bit more at the top, but in general, everything's being held in this stable emulsion, and it leads to poor separation in our wastewater treatment plants. So what are the physical impacts of surfactants in wastewater? Well, like I mentioned in the previous slide, they create stable emulsions, ultimately inhibiting or hindering separation process. This can be both in DAFs, in primary lagoons, or in primary clarifiers or sedimentation basins. They coat the biomass on both fixed film and suspended growth systems, ultimately suffocating the biology that's doing the work for us. They coat the water surface. They decrease surface oxygen transfer. They refract light that reduces beneficial algae growth. They promote the septic conditions that cause odors and the release of ammonia within the wastewater treatment. The surfactants also increase turbidity, oftentimes making it through the secondary process, and they decrease UV transmittance. They impact tertiary and reuse treatments. And once again, that increase in turbidity decreases beneficial algal growth in lagoons. So to throw back to a previous slide, we could see the difference between a impacted equalization basin covered with a stable foam and a film of surfactants, fats, oils, and grease over the top. And at the bottom, when we remove these chemicals from the wastewater, you can see a much healthier basin that's capable of transferring oxygen through the surface, but also this basin is free of odors and sepsicity. Next are the biological impacts of surfactants in wastewater. Some of you may be familiar. This is the GHS symbol for acute water toxicity. And if you look at the safety data sheet from most of these chemicals that we're talking about, you will see this symbol. So why does that matter to us? Well, most of these chemicals are coming to our wastewater treatment plant. So studies show that total inhibition of nitrification can occur at levels as low as 1.5 milligrams per liter of benzalkonium chloride on an unacclimated system. That's not a lot. Oftentimes we're seeing these concentrations at wastewater treatment plants upwards of 7 milligrams per liter. And even on acclimated sludge, 15 milligrams per liter will completely wipe out your biological system. So where do these end up in our wastewater treatment plants? Well, most of it is adsorbed to our sludge, both in the primaries and in the secondary clarifiers and the activated sludge process. So we're not getting rid of them necessarily, and we're not biodegrading them. Instead, they end up in our anaerobic digestion process, where they accumulate. They cause foaming issues. They inhibit methane production. If you're seeing sour digesters or frequent episodes of light foaming, it is likely due to these chemical compounds. Lastly, a lot of these chemicals are not removed through the wastewater treatment process, and they continue into our effluent. Well, surfactants contribute to both acute and chronic toxicity. benzalkonium chloride has a reported EC50 of less than 0.5 milligrams per liter. And many times it's 10 times less than that, depending on which report you see. So these chemicals are contributing to whole effluent toxicity tests and both acute and chronic toxicity. So one of the most expensive things within our wastewater treatment plant is providing air and oxygen to the biology. They're doing the work for us. This is the most impactful thing that surfactants have on wastewater treatment, is that they reduce oxygen transfer efficiency. Only 15 milligrams per liter of sodium lauryl sulfate, the most common of the surfactants in our consumer products, reduces oxygen transfer by half compared to clean water. That's extreme. But in most wastewater treatment plants, we see total surfactant concentrations coming into the plant of 20 plus milligrams per liter, sometimes 30 milligrams per liter. So what does this look like in our plant? And how does it create this inefficiency? We look at the symbol on the left. This is an unimpacted water body. There's nothing over the surface. There's nothing stable in emulsion. This allows very efficient oxygen transfer through the surface. And if we were to place a diffuser in the bottom of this tank, we would see the best efficiency that we could out of that diffuser. The next, in the middle, demonstrates what happens when fog and surfactants accumulate at the surface of a basin. If this is a facultative lagoon, there's zero oxygen transfer across the top, leading to septicity and odors. However, we can still aerate this system. There's still effective oxygen transfer with floor diffusers and fine bubbles, but you're definitely going to have odors and foam at the surface. But what represents our wastewater, and much closer, is the visual on the right-hand side. This shows that there's an accumulation over the surface, as well as those stable emulsions that we saw in that surfactant oil water triangle. In this situation, there is no surface transfer. And if we add a floor diffuser, we're still going to impede oxygen transfer. And we're going to show that in the next slide. So how do surfactants directly reduce oxygen transfer? So let's start out by looking at what a traditional fine bubble diffuser looks like. Here we see that as fine bubbles are created at the surface of the diffuser, surfactants are already attaching to the surface. These surfactants create a chemical obstruction of oxygen transfer through the bubble surface. They significantly decrease alpha factor. Smaller bubbles mean longer residence time as they slowly travel to the surface of our aeration basins, accumulating more surfactant, causing more obstruction, and further reducing oxygen transfer. Surfactants are the largest contributor to avoidable aeration efficiency. Therefore, they're creating the most inefficiency within our plants. That leads us to say, well, what is the industry doing about it now? This isn't a problem that a lot of people talk about, and it's not something that all of a sudden happened. It's something that's happened slowly. If you're in the food and beverage industry and you're treating their wastewater, you probably know about QACs. And so you're using chemical sequestrants. They bind to surfactants so they don't absorb to bubbles and biomass. Unfortunately, they still end up in the solids that go to anaerobic digestion process, causing foaming and inhibition and poor gas production. These chemical sequestrants are extremely expensive. And if you're discharging to a water body, it may require regulatory approval. Something that we do and we don't really talk about or think about, but we increase our SRTs. If we're not meeting our effluent performance, we increase the amount of biomass that we have under aeration. But increasing biomass also decreases the efficiency of your wastewater treatment plant, ultimately increasing aeration costs. Also, increasing biomass decreases your secondary clarifier capacity, creating overload conditions during high flow events and storms. Lastly, another one that we don't really think about, but we increase the amount of air that we put into our systems. Many surfactants on the good side are aerobically degraded, but typically within the range of 15 to 28 days. So we're not really removing them. But by increasing air, we're increasing our inefficiency. We're also adversely impacting selector zones, anoxic zones, anaerobic zones by DO carryover, and ultimately increasing energy costs. All of these are just a Band-Aid and don't go after the root cause. So with this, I'm going to lead to the next poll question. What do you do at your wastewater facility to mitigate the impact of these chemical compounds? Add metal salts to improve settling. Control odors with chemical or biological treatment. Increase the biomass in biological reactors. Use anoxic or anaerobic selectors. Oversize your clarifiers. Oversize the aeration system, or other. Please specify and write in your answer at the bottom. Looks like the majority of you answered increase the biomass in biological reactors. And that is, in fact, the most common way that we deal with it, is that the more biomass that we have, the more that we can ride through the shock loads that come into our treatment plant. Very interesting. Andrea, how does Moleaer's technology remove these inhibitory compounds?
Oh, well, it really comes down to the unique properties of the nanobubble. So Moleaer's technology generates a form of clean chemistry known as a nanobubble. Nanobubbles are roughly 100 nanometers in diameter, so 10,000 times smaller than fine bubbles, or the size of the bubbles that you would get from floor-mounted diffusers. Like larger bubbles, nanobubbles have a charged surface, and that surface is hydrophobic. But unlike larger bubbles, nanobubbles do not rise to the surface. They are neutrally buoyant and follow Brownian motion. This has to do with their size. Also, because of their size, they have an extremely high internal pressure. And it's these two properties that enable nanobubbles to do things that larger bubbles cannot do. Nanobubbles disperse in water, and they don't coalesce, and they don't rise due to buoyancy. They attract other hydrophobic materials like surfactants and fats, oils, and grease to their surface. They're also long-lasting, stabilized by the contaminants in the water due to that obstruction, such as we saw on the previous slide related to oxygen transfer in surfactants. Because they're long-lasting, they're able to interact with many contaminants in the wastewater. And they also have an extremely high internal pressure, 10,000 times higher than a fine bubble. So how does Moleaer's clean chemistry remove inhibitory compounds? Well, it goes back to the shape of those amphiphilic molecules. The hydrophobic head wants to be in the water, and the hydrophobic tail wants to be in another hydrophobic material, such as fats, oils, and grease, or the bubble. And since these surfactants coat everything, they'll coat the surface of the nanobubble. The nanobubble will accumulate the surfactants, and because Moleaer's technology injects hundreds of millions to billions of nanobubbles per milliliter, there's an enormous interfacial surface area of the nanobubbles in contact with the water to accumulate the surfactants. And when those bubbles destabilize, they release that extremely high internal pressure, more than 27.5 bar or 400 psi. That's enough to break the bonds of the molecules that have accumulated or the contaminants at the surface of the nanobubble. breaking apart these surfactants and changing the properties of the fat salts, grease, and surfactants. This helps to explain what we see on the primary clarifier in the photo below. The complete removal of that scum layer within less than 1 week of operation is due to the breakdown of those surfactant compounds that were creating that gel-like stable emulsion at the surface of the water. We go back to the impediment of oxygen transfer by sodium lauryl sulfate. At just 15 milligrams per liter, it reduces the oxygen transfer by half, meaning that that aeration system needs to be twice the size in order to deliver the oxygen required by the process. Moleaer's technology has been proven to remove over 50% of surfactants in raw wastewater, and this is independent of the surfactant charge. We're able to remove quaternary ammonium compounds, non-ionic, and anionic surfactants for a total surfactant removal of over 50%. You can imagine how much inefficiency is caused by the presence of these contaminants and how much efficiency can be recovered by using Moleaer's technology to remove these surfactants. This is why we can show these cost-saving benefits with confidence, and why we see year over year and project over project the reduction in energy costs on average of over 15% for treating wastewater. It also explains why we see these measured benefits and significant improvements in reducing aeration energy requirements, over 40%. And improving the effluent water quality results in less chemicals required for disinfection, saving over 40% on chlorine. And removing these inhibitory compounds from the wastewater also improves solid separation, increasing the solids that can go on to anaerobic digestion by more than 10%. And in our secondary treatment or activated sludge processes, all of this translates to significant more treatment capacity, unlocking up to 20% more treatment capacity within existing infrastructure. And lastly, removing these chemicals from the wastewater means that they can no longer bind with the solids that are going on to anaerobic digestion, improving methane production by removing that inhibition by over 20%. Moleaer's technology is simple to install, and it's offered with a CAPEX-free leasing option. This enables our customers to get the benefit of payback immediately. Typical payback periods when you use the CAPEX leasing structure are on the order of months instead of years. Moleaer's technology is known as a nanobubble generator. It's this piece sandwiched between the two spool pieces in the top. That piece manipulates the hydraulic properties of both the liquid, in this case wastewater, and the gas, in this case air. Requires a pump and a gas supply, and can be provided in a skid-mounted solution or a custom solution. We have mobile solutions and containerized solutions, and we can also go in line with existing pumps. We can do temporary installations as well. We have customers that have found a lot of value in utilizing Moleaer's technology to assist during construction to maintain plant operations and compliance. Ultimately, it's important to remember that this is clean chemistry. Nanobubbles are fundamentally different than larger bubbles. They do transfer some oxygen to the water, but when we're treating wastewater, it is not an aeration technology. Typically, a system like you see on your screen will only supply about 1% of what the process oxygen requirements are. And so it brings us back to our learner objectives and the key takeaways from today's webinar. We hope that with review of this webinar, you now know that Moleaer's clean chemistry is able to remove inhibitory compounds that disrupt wastewater treatment and cause significant amounts of inefficiency. Moleaer's technology can lower the cost of treating wastewater by using less energy and chemicals and footprint. This also translates to a significant increase in treatment capacity, as well as improved effluent water quality. Moleaer's technology is able to remove the inhibitory compounds that result in a lot of process instability, ultimately improving reliability and providing peace of mind to operators. Another benefit is the removal of the septic conditions. This translates to less odors, less foam, and less scum. And lastly, the technology can be easily integrated into existing infrastructure. If you have questions after this webinar, you would like to get in touch with us, please reach out to us at the email information provided on your screen. WP team, that's the water process team, at Moleaer.com. We're also going to be at WEFTEC and Polytech this year, and we'd love to see you at our booth. At this time, I'd like to open it up for questions and answers.
Thank you, Andrea. Appreciate that. That was great. We have another 18 minutes left, and I have a bunch of questions that are popping up. Please use the Q&A and not the webinar chat, please, so I can track the questions, and we will, if we don't get to all of your questions, we will make sure that we will send you a personal response. Question, and I'm trying to consolidate a few of them. Which industrial wastewaters do you have experience dealing with surfactants? Where do you apply nanobubbles in industrial wastewater plants?
Thank you, Baji. You want this one, John?
Sure.
Okay.
I can take this one. Which industrial wastewater do we have experience with? We've worked in both poultry slaughtering and in dairy wastewater. We actually have experience in other food and beverage industries as well. Typically, when we look at where we want to treat on a screened wastewater as early in the process as possible. So with most industrial systems, we're treating an equalization basin prior to the next process step. Sometimes that's before a DAF, before an anaerobic digester, or before an aerobic system such as MLE.
John, could you talk a little bit more about why you want it early? How much time do you need for the reaction?
Definitely. Nanobubbles are clean chemistry, and therefore, like other chemistries, there's a reaction time that's required. As Andrea talked about, nanobubbles are long-lasting in the water, and the longer that they're there, they can accumulate more of these hydrophobic contaminants to their surface and remove them. What we've found is that around 15 minutes is a great retention time to have nanobubbles in contact with the raw wastewater or the raw screened wastewater before it goes to the biological treatment process.
Right. Do you have any experience with dairy with an anaerobic digester?
Yes, we do. We've actually installed directly on an anaerobic digester and as pretreatment before it. What we've found is that nanobubbles interact very well in an anaerobic environment. In fact, it increases or decreases the amount of contact time necessary. But what's unique to Moleaer's technology is that we have very precise control of the amount of air that we're injecting. So we can make sure that we're not injecting too much air that would change the environment within the anaerobic digester. In fact, Moleaer's technology and nanobubbles will not impact your anoxic zones, your anaerobic zones used in biological nutrient removal and EPBR. What's unique and great about our technology.
Great. Hold on one second. Does it affect microbial communities in different samples? Can you drink nanobubble treated water or optimize output in biogas plants? There's many questions in there.
I think we've already touched on the biogas portion,
Yep.
but I will touch on how we impact microbial communities, is that if we can remove the chemical contaminants that ultimately select within these biological communities the least efficient biology. They're the least efficient biology because they're the ones that can survive the environmental impacts of these chemicals. When we can remove those chemicals, we do change the microbial community to the most efficient and really improve both on the anaerobic side and on the aerobic side. So when we talk about nitrogen removal, this is one of the major improvements that we see to the effluent, not just BOD and COD. So yes, we are changing the microbial community but naturally by removing the environmental stresses created by these chemicals.
And I can touch on the drinking water one. So I'll translate it back to water process. So we do have systems that are treating source waters for various things, such as algae and taste and odor and color. So we can treat the source water to the drinking water plant, if that helps to answer the question.
And one more side of that, I think that's really important to people, is that our technology is also used in aquaculture to provide efficient oxygenation and a healthier environment for fish. So, if fish can adequately consume and be in the presence of nanobubbles, there's really no concern over human use or EH&S concerns.
It's actually a good point, John. And for the audience, if you have questions, if you want to have a further deeper discussion, please don't hesitate to reach out to us. We'll schedule a one-on-one conversation and connect you with the right parties. Now, what effluent parameters is greatly affected by the technology aside from BOD and COD?
Sure. So I can take this, and then John, you probably want to expand on it a little bit more, but we do see significant improvements with nitrogen removal. And a lot of that's related to removing the effect of these contaminants on the biological community. So with less inhibition, you're unlocking more treatment capacity, you're able to more efficiently treat your wastewater. So we do see improvements in ammonia removal. We do see improvements in phosphorus removal, as well as nitrate.
Okay. So does the technology, sorry, John, did you have anything to add to that?
No, I think we've covered that pretty sufficiently.
And does the technology shorten the required retention time?
So the solids retention time, it does.
Yes.
So we see the mixed liquor suspended solids concentration coming down in response to nanobubble treatment. And that's where the increase in activated sludge treatment capacity comes from. That, in addition to more efficient oxygen transfer. So we're able to treat a higher load using existing infrastructure, or if it's a new facility, there's the opportunity to design it with redundancy where you can take treatment trains out of service because you're using the nanobubbles to provide a smaller footprint for the treatment.
Okay. Now, I agree with the case of some for industrial plants, but what benefits are in a normal municipal wastewater treatment plant? And in these muni plants, what extra energy is needed?
Sure. I think this is a great question for John. He can speak from his experience with the technology at the facility that he used to manage operations at.
Yeah, definitely. So municipal plants have really been our target market to this point because it's a more predictable wastewater stream. Even with industrial contributions, municipal wastewater is pretty steady. What we see is about 15 to 16% reduction in total plant energy indexed against the loading coming into the wastewater treatment plant. So if you have $1 million euro energy budget, we expect to see that decrease by about 16%. And so to touch on another question in the chat, and this one, the amount of energy that we need to put in is really based on the existing configuration. In many cases, we can install in line on an existing pump in which we're only adding a meter or so of head loss across that pump system. And so the energy in that case is negligible, and the amount of air we're adding is in the single digits of kW. If we have to add a pump, we're always dealing with low head, typically installing within a channel, a basin on an equalization tank. So we're talking very efficient pumps that we're using. And to touch on another question that's in there related to the technology is what is the expected life cycle of the technology? Our technology is really simple, which is great. your pump will not last as long as our nanobubble generator will. The biggest thing is that if we have a good, clean, screened source of wastewater, I know clean wastewater, it's kind of redundant, but as long as we can remove a lot of the large debris, the nanobubble generators operate hundreds of days uninterrupted and typically are being taken down routinely to be inspected. We do have a clean in place procedure that takes about 15 minutes of downtime, and that is only necessary every 3 to 6 months. So very easy.
Right. Both are related. I have two questions related to biogas and anaerobic digesters. Does nanobubbles increase biogas production in the digester? That you've already answered. We've seen 20% improvement. Is there a risk of explosion if we inject nanobubbles in the anaerobic digester?
So I can take that one as well. No, there's not a risk of explosion injecting nanobubbles into an anaerobic digester. The great thing is that nanobubbles themselves have so little mass of oxygen that even if one was to make it to the surface, the amount of oxygen that would be combining with biogas is insignificant. The other side is our technology does efficiently diffuse gases into the bulk liquid, but we go back to how little oxygen we're really putting in. The oxygen demand within the activated sludge or the anaerobic digested sludge exceeds the amount of oxygen that we're putting in on a huge scale. It's probably 10,000 times the demand in an anaerobic digester compared to the amount of air we're putting in. And then on the increasing biogas side, there's a lot of literature around the use of nanobubbles in anaerobic digestion and microoxygenation of anaerobic digestion to both increase the rate of hydrolysis, typically the first and rate limiting step, but also to decrease hydrogen sulfide formation and improve health. So definitely we've seen biogas increases on all of our facilities that we've been installed on, even when we're not directly on the anaerobic digester.
So there's the type of gas questions. Do oxygen or ozone nanobubbles perform better than air nanobubbles for selective oxidation of surfactants and fogs? And there's another question around gases. Do you use air or pure oxygen in aquaculture in order to prevent supersaturation?
Sure, I can speak to that. So in aquaculture, typically use a pure or a high purity oxygen gas supply to create the nanobubbles. And this is because they need more oxygen and sometimes higher levels. So it's just a process, configuration, design consideration. For the removal of surfactants, we don't need a different gas supply. We can remove surfactants sufficiently using an air gas supply. And air is easy to compress. Ozone is not. We do require a compressed gas supply. And then also, it's affordable. You know, air is readily available compared to if you're working with a high purity oxygen supply or a pure oxygen supply, or even an ozone gas supply. You're starting to add more ancillary equipment or a recurring bulk gas supply cost to your operating budget.
Great. Thanks, Andrea. Can nanobubbles be used in SBR systems where you have aerobic and non-anaerobic happen in one tank? Where is the best injection point? So
the best injection point is going to be upstream of the SBR. And yes, they can be used in that function because the nanobubble generator injects such a small mass of oxygen into the wastewater. We don't have to worry about dissolved oxygen bleed through to an anaerobic or anoxic process or sequence. So upstream of an SBR, you'll often find like an equalization basin. We're just looking for any wide spot in the process, whether it be a channel we can inject at a headworks facility inside of a channel or recirculating on a basin or tank. And then also for some systems, we're able to go inline if there is an intermediate pump station within the facility or a different pump station near the headworks that's downstream of screens. So really the only requirement is that the wastewater needs to be screened, and that's to protect the internals of not only the nanobubble generator, but also the internals of the pump that's providing the flow to the nanobubble generator.
What about injecting nanobubbles into dewatering systems? Would it not be beneficial?
We do see improvements on dewatering. And so looking to inject, going back to the anaerobic digester question, I don't necessarily have to inject on the anaerobic digester. If there's a tank for thickening the sludge, we can inject on that tank, for example. So as long as there's a tank available, there's a location where nanobubbles can be injected, usually on the solids streams. Otherwise, by pre-treating, I could just say by pre-treating the liquid stream, you're also treating the solid stream, because you're keeping those surfactants from accumulating in the solid streams in the first place. But for facilities that are specifically configured or interested in treating the sludge streams, we can directly treat the sludge streams as well.
Is the oxidation of target contaminants like surfactants localized to the discharge point of NBG?
So when the nanobubbles are formed within the nanobubble generator, that's when they are stabilized by the contaminants in the water. So the attraction of the surfactants to the surface of the nanobubble happens instantly. But the nanobubbles destabilize due to different interactions with different energies, whether it be energy from UV, like sun coming in through the surface of a basin, for example, or mixing energies due to floor diffusers, or just other interactions within the water. Those are the energies that will destabilize the bubble. And it's not until the bubble destabilizes that these compounds are broken down. So that's why you have that 15-minute reaction time. Typically, we see about that 50% removal within a 15-minute period. But yes, the binding of the materials or the sorbing of the materials to the surface of the bubble does happen fairly instantaneously.
Yeah. Could you explain what are the typical CAPEX costs for an average system, and also explain nanobubble as a service? You touched on it on a slide.
Sure. So the CAPEX question really depends on the size. So since we have both low flow and high flow systems, and facilities are all loaded differently, this is a load-based technology in terms of how we size for it. So if you would like to get CAPEX for your specific site or installation, please reach out to us at the WP team at Moleaer.com. We'd be happy to get you pricing. Otherwise, the range is so large and dependent on many factors, such as whether or not a pump needs to be included, as well as the gas supply. And then in terms of the CAPEX-free leasing option, some of the benefits that we see there as well is that we're continuously innovating on technology. And, like I mentioned earlier, a couple of years ago, we didn't have a high flow nanobubble generator. We do now. We continue to develop methods and technologies that produce higher concentrations of nanobubbles. So as new generations of the technology become available under that leasing option, you're able to swap the technology for the latest version.
A couple more things to add there. We do not have the leasing option outside of US, Canada, and European Union. So if you're outside of that region, it will have to be a CAPEX. And on the CAPEX side, it also depends on the flexibility, i.e. we can put 2 units in parallel or multiple units in series to replace larger units. There's a lot of many different configurations. So please feel free to reach out, and we will get you the right business development manager to talk to you about it. And can nanobubbles replace the requirement of nitrate chemicals in upstream sewage pipes feeding the plant?
John, I think this one is for odor control.
Yeah, definitely. So we've seen great results from nanobubbles being injected as early on as possible. This is up into the collection system, helping to reduce chemical needs for H2S. One of the challenges comes is that we prefer to make nanobubbles in situ, which means that we want to use the wastewater and a pumped flow of that wastewater to create the nanobubbles. This requires that we have screening before the pump in the nanobubble generator, which is the hurdle that we have to overcome for collection systems. But this is definitely something that is on our radar. And as we develop new technologies, we definitely have a focus on providing a technology for the collection system in the future.
We are 3 minutes past our time. I'm going to extend it by 2 more minutes. Couple quick questions. PFAS. In short chain PFAS molecules, are there nanobubble impact?
That's I want to call it the $1 million question, but I think it's worth a lot more than that. We have reason to believe that there's value to be had by combining nanobubbles with PFAS removal technologies. We're in the early stages of our own work here with that in R&D, but always looking for good partners to develop that with. So if you're specifically interested in PFAS, please reach out to the WP team, and I will help to connect you with the right people within Moleaer.
Yes. And then a dewatering purpose, do you use nanobubbles previous to DAF units?
So specifically for dewatering, DAFs, I'm not sure that we've done that, but we do have many nanobubble systems operating in combination with DAFs, either pre-treating them or actually injecting on the DAF itself. And some of the benefits that are observed on DAFs, and of course, it's all dependent on the nature of the waste and the chemistry of the DAFs, because DAFs are rather complex in chemistry. But we do see thicker solids, so a thicker mat with less water in it and better dewaterability. So I would think that if you were pre-treating a DAF or treating a DAF that was, let's say, used for municipal sludge, that there would be the potential to improve the dewaterability of those solids as well.
I'm going to ask this as the last question, and the rest of them we will respond to you separately. Can nanobubbles oxidize residual polymer flocculants?
I am going to say that is unknown at this time.
All right. Thank you very much, Andrea and John. Wonderful presentation. And thank you all for the participants, for listening in and staying through the event. We have about 90% of the people still remaining. That tells you that's good. We will come back to you guys with a recording of this webinar. We will also come back to you with any questions that have been unanswered. And please feel free to meet with us in WEFTEC, which is next week. Pollutech in Lyon is the week after. So we will be there. We will have a nanobubble generator to show and tell. You can see it. You can see the simplicity. And we will put this presentation. I expect this to be out and about in about a couple of weeks. We just have these couple conferences coming up. So please feel free to reach out in the meantime. Thank you all. Have a wonderful rest of the day.